Right. It's a few minutes past 5 here in Australia, so I suppose we can start. Welcome, everybody. Good morning, good afternoon, good evening, depending on where you are in the world. Hello from Sydney. I'm Christos Pliatsikas, and I am here to welcome you to the first workshop of the International Symposium of Bilingualism, which is a satellite workshop on an introduction to advanced statistics for language sciences. This workshop was generously funded by the British Academy, and we have a range of speakers talking to you about different topics in advanced statistics. And in the next slide, you will see the schedule of today's workshop. So we will start the first session with an introduction to mixed effects models in bilingualism research. This will be a live session delivered by my colleagues Ian Cunnings and George Pontikas from the University of Reading. This would last for a little under an hour and will be followed by a Q&A session. Then after that, we have a session on generalized additive models in R, or GAMS. This is delivered by Stefano Coretta, who couldn't be with us live today, but he provided very kindly a recording of this session, which I will play. This will be followed by a session Bayesian analysis for bilingualism research by João Verissimo, who is here live with us. This will also be delivered live. And then this section will also be followed by a Q&A session on both GAMS and Bayesian analysis that will be delivered by João as well. And that will bring us to the end of this workshop. So I guess without any further ado, I will hand over to Ian and George for the first session of the workshop.
Hey, thank you, Christos, and thank you for the introduction. So as Christos said, our first talk today is an introduction to mixed effects models in bilingualism research by me, Ian Cunnings, and George Pontikas. I should say that this is a presentation that comes in two halves. In the first half of the presentation, I'll provide a more conceptual introduction to mixed effects models and why they might be useful for researchers interested in bilingualism. And in the second half of the talk, George Pontikas will take over to go over some practical examples of how we can use mixed effects models to do analyses in R. If any of these stuff that I introduced sounds a bit technical and difficult in the first part, hopefully by going over an example with George in the second part, things will become clearer. Okay, so to start, an introduction to mixed effects models. I think it's true to say that bilingualism researchers often face particular challenges when attempting to generalize study findings beyond their own sample. I think this is generally true in psychology and language sciences recently with the problem of the replication crisis, but it kind of gets compounded in bilingualism research because we can never really be sure if a finding doesn't replicate, whether it's because the finding isn't true, it was a false positive, or perhaps there was something different about the populations that we've sampled that explains why why something didn't replicate. Another problem that we might find is that study samples are not always truly random. It's typical, for example, to run experiments on university students that may not be truly randomly sampled. And in particular, the data may cluster, the observations that we make may cluster in different ways. And here's an example that you might find if you're an applied linguist looking at language teaching. You might test a strategy for language teaching and test a bunch of students in a bunch of classes in different schools. But these observations from different students are not truly random because students are clustered into these clustered hierarchically. So students are kind of clustered in classes and they're clustered in schools. And it might be that students in a particular class behave in a way that students in another class don't. I think it's also true that researchers in bilingualism often have to deal with very heterogeneous population samples. It's also true that if you're studying monolingual language processing, there's heterogeneity in the population that you sample, but it's kind of compounded more if you look at bilingualism or multilingualism because of the more complex language backgrounds that you may have. So in bilingualism research, participants both within and across studies may differ in non-trivial ways. So, for example, their language background, their proficiency, the age of onset of the different language they know, the length and type of exposure, motivation, where they use the language, code switching behaviors, and so on and so forth. Also, it's also possible that bilingual samples may sometimes include more missing data than in comparison groups. Here I'm kind of thinking of research that compares native to non-native language processing. If you're to do a simple lexical decision task where you want participants to respond quite quickly, so you have a timeout, the non-native speakers, because they're a bit slower, may be more likely to reach that timeout, which will then be treated as missing data. So despite this variability and variance that we might be interested in, traditional analyses used in bilingualism research and indeed in the language sciences more generally often involve averaging across individuals. So if you do your bi-subject ANOVA or a bi-subject t-test or correlation, what you would typically do is you would repeatedly measure a participant on various factors, and then you'd average across your conditions. And this averaging across participants is problematic for two reasons. Firstly, if you average, you're underestimating the true variance within your condition. So if you have 8 participants see 20 observations in each condition, and then you average, there's variance there that you're ignoring, basically. And this can potentially lead to false positives and believing an effect is true when it's actually not the case. I should say that this averaging isn't just a problem from the kind of perspective of the statistics police saying you're doing your analysis wrong. Often we are actually interested in this variance, and by averaging, we are losing variance that we may want to explain. So again, in lots of areas of the language sciences, I think over the last decade or so, people have become interested in individual differences. And this is obviously the case in bilingualism research, where the heterogeneity of the participants we sample is often something that we're interested in explaining. So by averaging, we are reducing the variance that we actually want to explain, and which may actually be our research question and our hypothesis. Some other further limitations of traditional analyses, including they have difficulty with imbalanced design. So technically, you should have roughly the same number of participants in the different groups that you're testing. And also, the traditional analyses do not account for the clustering of data in certain ways. It's obviously true that if you do a repeated measures ANOVA or a paired samples t-test, the analysis takes into account the clusterings of your data in that you have 2 observations from the same participant. But the data may also cluster in other ways that traditional analyses can't really deal with adequately. So consider as an example again, a typical design you might see in applied linguistics and second language teaching, in which a teaching strategy is tested on a group of students in several classes within a school. So you test the strategy on loads of different students in school. If you average across students, ignoring the fact that they come from different classes, you may ignore correlations between students that are clustered within each class. So student performance may vary by class, some classes may just be better, and that's regardless of what you're actually interested in. So here, the data from each student within a class is not truly independent, which can lead to false positives. And we ideally should try and model the independence between, the dependence rather, between data within classes and schools. So mixed effects models provide a way of analysing data that does not require any prior averaging and allows us to overcome some of these limitations. For example, mixed effects models allow us to model individual variation and individual differences in a way that we can't really do if you average your data first. And mixed effects models are also more robust against missing data, assuming that the data is missing at random. Mixed effects model also provide an explicit way of modelling how data may be clusters in theoretically important ways. And also we can use different so-called families of models to analyse different types of data. So you can use different types of mixed effects models to analyse a continuous dependent variable with different distributions. You can analyse binomial data or ordinal data, etc. And I think when we think of traditional analysis, we think, right, if I have a continuous variable and factors, I need to use ANOVA or a t-test. If I have If I have a continuous variable, I need to do a correlation. If I have a binomial response, I need to use logistic regression, as if they're different types of analysis. But actually, the statistics underlying all of these analyses is actually very similar, and mixed effects models kind of emphasizes this by allowing us to pick whichever family of analysis we need to do based on our data and our independent variables. So what is a mixed effects model? So a mixed effects model is a statistical model that contains both fixed and random effects. I should say that technically the more traditional methods can be fixed in that you can do a mixed effects ANOVA with both fixed and random effects. However, in more recent literature, the term mixed effects model has really been reserved for the class of statistical models that explicitly allow the modeling of different types of fixed and random effects and different types of random effects that I'll go into in a moment. These types of analyses come under various different names. You might see the term multi-level model, hierarchical model, nested model, and so on and so forth. But for present purposes, I'll just use the term mixed effects models, and I aim to cover the different types of the different names of these models. So what is a fixed and random effects, and how do we define the difference between fixed and random effects? It's actually not as easy as it sounds. The famous statistician Andrew Gelman from Columbia University, for example, has several blog posts on how it's actually difficult to define these terms and how he doesn't really like these terms. So depending on which book you read, you might find different definitions. But for present purposes, I'll just try and explain it with an example. Consider you're running a study testing 2 English language teaching strategies. You have 2 groups of students, and each are taught with one of the strategies, say strategy A and strategy B, and the students are also tested on a proficiency test both before and after this course of teaching that they take. And what we're really interested then is the differences in scores in the proficiency test as an indicator of which strategy, if any, are indeed better. So here our independent variable would be teaching strategy, and our dependent variable is scores on the proficiency test. So how does this relate to fixed and random effects? So the independent variable of interest, language teaching effect, is modeled with a fixed effect, and any random variance that we're trying to account for in the students sampled from the wider population will be modeled by a random effect or several random effects to try and account for the way the data may be clustered. It's important to note that mixed effects models can have different types of random variance, and so we have different types of random effects. And so the main 2 I'm going to talk about today are the difference between nested random effects and crossed random effects. So hierarchical or nested random effects model clusters of observations that are organized into some sort of hierarchy. So for example, students might be hierarchically clustered into classes, and then these classes themselves may be hierarchically clustered into schools. So we can think about the kind of nesting and the hierarchical clustering of the observations here. Crossed random effects model clustering of observations at the same level of the hierarchy. So for example, you may have students clustered within classes within a school, but then you may also have students from the same family, and students are hierarchically organized into families. You may also have students from the same family in different classes. And so what we would say here is that families and classes are crossed at the same level of the hierarchy. So to illustrate this, consider a toy example here of a school, and these people are supposed to represent the students. They may be organized into 3 classes, I'll call them Class A, Class B, and Class C. So we can see here that these 4 students in Class A, 4 students in Class B, and 4 students in Class C are all hierarchically organized into classes, and then these are all hierarchically organized into the school underneath. But it might also be that some of the students from the classes are from different families. So you might have these 2 red people here that come from the same family. I'll call them family A. These you might have 3 people here, these green people, and they all come from, let's say, family B. You might have more other things as well. So we see here that students are hierarchically organized into classes, but they're also hierarchically organized into families. And importantly, families and classes are crossed at the same level of categorization. What I mean by this is that you have different students can appear in different classes from the same family, and also students from the same family can appear in different classes. So classes and families are crossed in this example. This cross nature of random effects was of particular interest in the language sciences over the past 10 to 15 years, because it provides an innovative new solution to the language's fixed effects fallacy that was proposed by Clark way back in 1973. So what Clark observed is that the human subjects in any language experiment are sampled from the population of language users. If I test 30 subjects, they're obviously not all of the subjects that they're obviously not all the subjects, they're sampled from a population. However, as Clark also noticed, we can also say the same thing about the linguistic materials that we test, in that the linguistic materials that we test can be considered as being a sample from the populations of materials that have the same characteristics. So, for example, say I did a simple experiment looking at the garden path effect, where I create 20 sentences, 10 garden path sentences and 10 non-garden path sentences. These are obviously not all of the garden path sentences that exist within the language. They're only a sample of the possible garden path sentences that exist. So we need to think of not only human subjects being sampled, but also the linguistic items as well. And so to be confident that study findings generalize across both people and also linguistic materials, both sources of random variation need to be taken into account. To emphasize this, consider this hypothetical small data set here. We have 6 columns, and each of these columns is intended to represent a subject, subject 1, 2, 3, 4, 5, and 6. The numbers here represent reaction times, for example, in a simple lexical decision experiment. These subjects were repeatedly measured in what I'll call condition A and condition B. We can see each subject sees 4 items in condition A, items 1, 2, 3, 4, and 4 items in condition B, items 5, 6, 7, and 8. If we do the traditional way of doing analysis where we average by subject, we might find, for example, as in this case, that all of the subjects show the same effect, in that condition B has longer reaction times by average reaction times by subject than condition A. The 588, 619, 513, 544, and so on and so forth. So if we were to do a paired sample t-test, if we had enough participants, this would likely yield a significant by-subject effect, and we might say here we have clear evidence that condition B is significantly longer than condition A. However, we also need to account for the items within the analysis. So not only averaging by subject, but also averaging by items as well. And we can do this simply here. So here are the averages calculated for item 1, 2, 3, 4, 5, 6, 7, and 8. In condition 8, you can see the by item averages are all about roughly 550 milliseconds, give or take about 20 milliseconds. And if we look in condition B, 3 of the items are actually behaving the same. So 3 of the items here are roughly 550 milliseconds. It's just this one item, item 8 in condition B, that has much slower reaction times. So what it seems to be here is that this isn't really a true effect, in that condition B isn't really much slower than condition A. The by subject effect is entirely carried by this rogue item, item 8, which suggests there's something about item 8 that's causing this effect, not the condition, condition B. So this illustrates the point Clark made that we need to consider random variance from both subjects and also items. So how do we account for this issue in language research? Well, traditional statistical methods would involve researchers conducting 2 analyses. You do your F1 or your T1, in which you average data over subjects, and then you do your F2 or T2, in which you average your data over items. And if they're both significant, you say, yes, I found something. However, while the F1 or T1 analysis takes into account by subject variation and F2 takes into account by item variation, neither takes both sources of variation into account simultaneously. Mixed effects models, however, with cross-random effects for subjects and items provide a better solution, and they provide a way of taking into account both sources of variation in a single statistical model. So there's been a lot of increased use of mixed effects models in language research over the last 10 to 15 years. One of the main reasons is to come over this language's fixed effects fallacy. I should also note, finally, before moving over to George, that random effects can further be categorized into different types of random effects, namely random intercepts and random slopes. And you should carefully think about whether or not to include random intercepts and random slopes in your analysis, as this can impact on the conclusions that you draw from your data. So what is the difference between a random intercept and a random slope? Again, we'll do it by an example. So consider a simple lexical decision experiment examining the word frequency effect. Participants make a series of lexical decisions to words in 2 different conditions, and their reaction times are recorded. So you say you have low frequency words and high frequency words, and we expect low frequency words to have longer reaction times than the high frequency words. Participants in this type of experiment will vary in 2 important ways. Firstly, some participants on average will just be quicker or faster than others. So some participants on average will be very fast. They'll have an average reaction time overall, irrespective of condition of say 500 milliseconds. Another participant might have an average reaction time closer to 1 second. So this difference in average reaction time across participants would be modeled by a bi-participant random intercept. Participants may also differ in the relative size of the effect, i.e. the relative difference between the two conditions. So some participants may show a very small difference between low and high frequency words. Other participants may show a very big difference between low and high frequency words. And it's this difference between the size of an effect that is modeled using something called a random slope. So a random intercept models average by subject in this case by subject variance, while as a random slope is estimating the difference in the size of an effect. Random slopes can be included for any repeated measures variable. So if you ever have a repeated measures, you can include a random slope. For between subject or between item manipulations, random intercepts would suffice. And I would say when you think about whether or not something is a repeated measure or manipulated between a unit, you need to think of it not just for your subjects, but also for your items. Sometimes one thing will be between subject item and a repeated measure for items, or vice versa. So you need to think about the random intercepts and slopes for both subjects and items. I should say there is debate in the literature regarding how and when different random effects, especially random slopes, should be included. Some have argued for what I would say is a more data-driven approach, for example, Matthew Sheck et al. 2017. And if you've read Bayern's Introduction to Linguistics in R, I think he often takes a more data-driven approach to analysis. Others have argued that you should take a more theory-driven approach, especially if you're running a confirmatory study where you've manipulated specific variables that you're interested in. I should say that there is currently there isn't a consensus on which way to use, and I think which one you use will likely depend on your research questions and hypotheses. I would say as long as you have good motivation for the method that you use and you clearly explain what you're doing, you should be fine. So before turning over to George, I'll just quickly describe what I mean by data-driven versus theory-driven approaches to random effects. So according to the data-driven approach, you only have to include a random effect, and in particular a random slope. You should only include it if it significantly improves model fit over a model without the random slope. So what do I mean by this? So the idea here is that you would fit two statistical models, one containing, for example, just a bi-subject random intercept, and another one containing the bi-subject random intercept and also a relevant random slope. You would then do some sort of model comparison to see if one of the model provides a better fit to the data. And a typical way of doing this is by running an ANOVA comparing the two models. Then if the random slope significantly improves model fit, you would include it in the model. But if it doesn't, you wouldn't include it. One thing I should say here is to consider what threshold you use for significance when doing this sort of comparison. So Matthew Sheck et al., for example, use a less conservative threshold when they're assessing the random effects, a P of 0.20, than you would use when assessing fixed effects, your independent variables, where you use the typical 0.85. On the other hand, there's what's called the theory-driven approach, which argues that you should add random slopes should be fit using the maximal random effect structure justified by the design. So this argues that you should include all relevant random intercepts and all random slopes for all repeated measures that you manipulate. So the idea here would be that if you have, say, a 2x2 repeated measures design, you need to include random slopes for the two main effects and also the interaction. The issue here, however, is that these complex models can sometimes lead to problems in that they don't converge. A model that doesn't converge basically had difficulty fitting the data, it's too complex, and it just fails. So you end up with models that are too complex for the data that you have, and then you have to simplify the model in some way, and George will go over an example. Personally, although there's no consensus, personally for me, if you're running an experiment where, say, you have a 2x2 design, I would initially try and fit the maximal random effect structure because I've specifically manipulated these variables for a reason. If it doesn't fit, I might simplify the model. If I'm doing a more exploratory analysis where I might be adding in all sorts of individual differences measures, including random slopes for all of these effects will get too complicated. And in that case, I might use a more data-driven approach. But as I said, I think it will depend on the research questions and hypotheses that you have. Okay, that's the end of my part. Now George will take over and go over some examples to help illustrate some of these issues that I've discussed. Hopefully we'll be able to, I will stop sharing and hopefully George will be able to seamlessly start sharing his.
Okay, so I'm going to start sharing my screen now. Can we all see? Ian, Christos, are we okay to start?
Yeah, but you're not in presenter mode. I can just see all your slides.
Okay, let me see. Presenter mode. Which is sorry, no.
You might want to go to display settings, George. Yeah, there
We
you
okay
go.
now?
Yeah, that's right.
Okay.
Yeah.
Okay, so perfect. So hi, and welcome me to the second part of the session. Here we're going to have a look at a couple of practical examples of how we can use mixed effects models with data sets that would be relevant to linguistic research. We're not going to actually run the models in real time, but I'm just going to show you what you would do and what kind of output you would get. Now, we're going to work with an example from a hypothetical data set, and this was assumed to be a study on garden path sentences. So those are sentences that have local ambiguity, as you can see in the examples. Example 2 is the actual ambiguous sentence, and example 1 is the unambiguous control, which is disambiguated through punctuation, i.e. with the comma. Now notice that the two sentences have exactly the same pairings of words, so Anna, baby, and the verb dressed, and this is an example of an item, and in a study we would probably use multiple pairings of sentences like these, which we would call items. So this study included 40 native English speakers who read 24 experimental sentences in a Latin square design. And each participant saw 12 non-garden path sentences and 12 garden path sentences. And what we measured was how fast they were to press the button to move on to the next segment when they encountered the critical word play, the verb played, which is where you get the disambiguation and where you'd expect people to slow down in the event of ambiguity. Now, in addition, R has some basic functions which we use, but you can also have some additional packages that can be installed, and these provide more advanced functions for various analyses and data visualization. Now, to be clear, the example that we've included, it only has native English speakers. We don't cover between subject comparisons in this presentation. That is perfectly doable with mixed effects models in the same way that you can do an ANOVA that's simply between subjects or with repeated measures or a combination of the two. So the three packages that we'll be using in today's presentation are LME4, which is for linear mixed effects models. That by default doesn't produce p-values, which disappoints a lot of psychologists. So for that reason, we'll also be using the LMER test, which computes the p-values for mixed models. And we'll also be using ggplot for advanced data visualization. Now, the data, most of the data you're going to use in R for mixed effects, for the purposes of mixed effects modeling, is normally in text file, but you can also you can load data from Excel files and from SPSS files. But for TXT files, you would use the read table function, and you can see an example of what the code would look like below. Now, you can also use the head function to get a preview of the data, and normally you get the first 6 rows and the type and the name of the columns. So here you can see 4 columns, subject, item, condition, and RT, and the first 6 rows. Notice that the data are all from the same subject, so subject number 1. And this means that it's not the case that we have 6 different conditions. Actually, we have multiple data points per subject per condition. So you can see in the first 6 rows, 4 data points from the no comma condition and 2 from the comma condition. And the comma condition is the unambiguous control. Now, this is just the first 6 rows. If you could scroll down and see the rest of it, you'd see that the data are more balanced. And then you have the column RT, which is the reaction times for this particular critical segment that we're interested in. And for the purposes of this demonstration, is going to be our dependent variable for most of the examples that we're going to use. Now, just a reminder that of what a regression model is, because a linear mixed effects model is essentially a regression model with some additional complexity that it has random intercepts and potentially random slopes. A regression model is a function in the form of y, or f of x equals a plus beta x plus epsilon. Now, the y is the dependent variable that you measure, what you actually observe. The A or the alpha is the intercept. So it's the average value, or when beta is at 0. Beta is the slope, or B, and this is the change that we get for every change in our independent variable. And it results in change of quantity B in our dependent variable. So for example, if you think of the example, we're trying to figure out how much our effort for a particular course results in a grade, we'd have a model of the form. You'd have some starting value, which is, I don't say 30% from simply attending the classes, and then you could assume that our performance would improve, say, by 1.5% for every 2 hours that we study outside the lectures. And then the epsilon, or the E, is the error. Then that's the difference between the predicted value of the model minus the value that we actually do observe. So a mixed effects model is just that, except that it allows the alpha and the beta to vary. So the starting point could vary by subject or by item, and the actual effect could vary by subject or by item. So to fit a mixed effects model, we would use the LMER function, and I can give you an example. You can see an example here. We're creating model.example1.1, and that is an LMER model. The RT, which is the first thing we've written in brackets, is the dependent variable, and the tilde then shows what are the independent variables afterwards. So we're modeling RT on condition, which is the fixed effect. And then you notice that we've added one vertical line subject plus one vertical line item. And this specifies that we're allowing cross-random effects by subject and by item. So we're saying that fit this regression, but allow the alpha to vary to allow all the participants to have a different alpha and all the items to have a different alpha. And then we're specifying in what data set we would like the model to fit. Where do we want the data to come from? And in this case, it would be the data frame data.example1. Now, the current model only includes random intercepts for subjects and items. This means that we allow for the average reaction time for each subject and each participant to vary, not yet whether the slowdown or the increase in reaction times will vary by subject or by item. We can also include random slopes to account for the differences in the size of the garden path effect across the subjects. And in this case, we're working on the assumption that garden path sentences will cause a slowdown, so that will be an increase in the reaction time. So we can say that our subjects and that each of our participants will have an average reaction time that will vary, and each pairing of words will have a reaction time that will vary if we have random intercepts. But if we add random slopes as well, what we're saying is actually the difference between ambiguous and unambiguous can be different for each of our participants, and the difference between ambiguous and non-ambiguous can be different from across the different pairings of words that we have. So go back to the last one, to what some of the last slides from Ian with the reaction times by item and by subject. So how would we actually specify that we want random slopes to be included in the model? We'd normally put in brackets 1 plus condition vertical line subject, or 1 plus condition vertical line item, or the two together, which would be plus. So this is basically telling us include a random slope, a random intercept, and a random slope for each of these two. And if we want random slopes for each of these two, what we assume to be random factors, so the subject and the item, we have to specify them separately. If you want to see the result of your model, you have to use the function summary and specify which model you want in the brackets. If you just run the model, you'll get the output, but you won't see it. So here is how we would summarize the model that we've previously fitted. Notice that the model starts with random effects, and these are the random effects that we have specified. And you can see that we specified 2, subject and item, and then look at the second column, which is name. And you can see that it contains the intercept twice in brackets. Now, what it's saying is you fitted a random intercepts only model. These are the random effects that you're getting for the intercept by subject and by item. And then in the column variance tells you how much variability there is by subject or by item respectively for each of the 2 rows. And the standard deviation gives you an estimate about how much variability on average, and the standard deviation gives you an estimate of how much variability there is in the difference between the average reaction times for each subject and each item. And then below that, you see the fixed effects, which is what you would normally get if you were running a t-test or an ANOVA or a regular regression. The first row is the estimate of the average intercept. So row that says intercept, that's almost always likely to be significant. And the second row is the effect of ambiguity, so the difference between the garden path sentences and the unambiguous controls. So the column estimate gives you the average, gives you the estimated average value. So we can estimate that on average, every participant is going to need about 444.67 milliseconds to respond at this particular segment. And the second row, which is the slope, means that there will be an increase in reaction times of 153.16 milliseconds when we go from unambiguous to ambiguous. So the no comma is the ambiguous sentence. The second row is the standard error, and this again is a measure of the variability and the uncertainty around this average estimate. After that, you get the degrees of freedom, and then you get the t-value. Now, what is the t-value? It's a t-test to test whether the intercept is significantly different from 0 and whether the slope is significantly different from 0, which is exactly what you would have in a standard fixed effects, bog standard linear regression. And then the last rightmost column, the PR, is the p-value, which you will really want in psychology, and that's debatable as to whether it's best practice or not. And you can see that both of them are significant, very, very significant. So the p-value would be below 0.001. And the more variables you add, the more rows you will get with exactly the same estimates. Well, a one estimate for each, a t-test for each, degrees of freedom for each, a standard error for each, and a p-value for each. Now, that was the summary for the model with random intercepts only. If you want to fit a model, we did just fit a model with random slopes as well. You would summarize the model in exactly the same way, and the output would look almost structurally identical. So you can see, first of all, it presents the random effects. What's different here is you can see the random effects for the intercept and the slope by subject and by item. So you don't get 2 rows, one for subject and one for item. You get 4 rows, 2 for subject, 2 for item. One is with intercept, which is the random intercept by subject and slope, which is what we saw in the just now. And the second row for subject and item is the random slope by subject and item. So how much each participant, what variability you get in each participant in terms of the slope, and how much the slope varies for each item, i.e. the lexical pairing. And again, you see the variance and the standard deviation around this average estimate of the variance. Notice that you get a third column, which is the correlation between the random intercept and the random slope, which you can remove if you want by adding 2 vertical lines when you specify the random effects. And then below that, you get the fixed effects, which is what you did previously, and which is what you would get in a regular regression model. You get the estimate, standard error, degrees of freedom, t-test and p-value for the intercept, and you get the respective values for the overall average slope. Notice that the estimates change a bit. That happens when you change the model, but for this particular model, it doesn't change the fact that there is a significant the intercept is significantly different for 0, and that the slope is significantly different to 0, which means there is a significant difference between ambiguous and unambiguous sentences. So moving from an unambiguous to an unambiguous sentence, from an unambiguous to an ambiguous sentence, there will be a slowdown. There will be an increase in the reaction time. So in the intercepts only model, it was 143 milliseconds. Here it's 148 milliseconds. So what we're interested in wouldn't change that much. Now, we have 2 models, and the question is, well, which one should we report? And best practice is to report the best one. How do we establish the best one? You can get various model fits such as Ike, BIC, and R², but one thing you would want to do is test whether the 2 models are significantly different from one another. What you would do is you would use the ANOVA function, and in brackets, you would specify the 2 models that you'd want to compare. So in this case, this is what you would write in order to compare model.example1.1, model.example1.2, and it would refit the models with a slightly different algorithm. It tells you again what each model looks like. And then below that, you can see the model comparisons. And as I said, you can see the archaic information criteria, the AIC, you can see the BIC, you can see the chi-square, and you can see the probability. And notice that the probability is again significant. The two models are significantly different. The p-value is below 0.001, and this suggests that the model fit with the random slopes is a better model, and we should probably be reporting that one. Generally, that's very likely to be the case, that including models with random slopes are better models. In terms of whether it actually leads to really different results, in my experience, it probably doesn't. The only thing is, its conception might be better to use to include random slopes to account for the fact that, well, this effect might vary especially by subject, less so by item, and by doing this, you actually you reduce the impact of outliers as well. Now, one thing we should be doing is we should actually check whether the model is whether the data are really suitable for the model as we viewed. So we can use the dot plot function to look at the random effects, and this is, you can see here how we'd write it. We'd ask for the model the random effects to be produced for this particular model.example 1.2, and you'd create a dot plot by subject, and this is what you can see here. And you can see that there's quite a lot of variability both in the intercept and in the slope. So for the intercept, you can see that the fastest participant would have an intercept of over 300 milliseconds. The slowest participant would be 300 milliseconds slower than average, but the fastest one, so participant 6 at the bottom, would actually be about 150 milliseconds, nearly 200 milliseconds faster than average. And then you would get the same thing for the slope, which is in the rightmost column. You can see that for participant 34, there's a slowdown of about 300 milliseconds, but for participant 6, the slowdown is actually 100 milliseconds smaller than average. And you can do this both by subject and by item. So in the example I just mentioned, I plotted them by item. You can also do it by subject. You can also do it by item, simply by changing the subject to item. And this is the output you would get. Notice that you get much less variability for both the intercept and the item for the slope relative to what you would get for the to subject. So participants vary a lot more than the individual stimuli that you've had in, I think, a lot of studies that I've seen at least. Now, like an ANOVA, standard mixed effects models assume a normal distribution of the data. Technically speaking, it's not the data themselves that need to be distributed, it's actually the residuals that need to be normally distributed. So the difference between the predicted value and what you actually observe. How can you test this? Well, you can plot the residuals. You can ask R to create the residuals of the model.example 1.2, and you can plot them by using the function qplot, and you could get something like this, and this does not look very normally distributed. You could also try to look at the normality of the distribution of the residuals using the QQ-norm function, which is written in exactly the same way. And in this case, it gives you something like this. Now, notice this is not a particularly, this indicates that the data are not really normally distributed. What you would expect is a more straight line, a more straight line increasing. Now, if the model residuals are not normally distributed, it might be that the data themselves are not normally distributed. What you can do is, and here is an example of, here's how you would plot the actual data themselves. You would ask it to produce a Q-plot or produce a QQ-norm plot, not for the residuals, but for the particular data themselves. So the data you would get in the file data example 1, column RT. Now, one way, if we do get this, one thing we can do is to apply a log transformation to the data, and this normally reduces the skew in reaction times, and it's used mainly for reaction time data. So what you would do is you would ask R to log transform this particular column, so data frame data.example1 column RT, so the $ suggests the particular column in the data frame, and you would ask R to produce a Q-plot or a QQ-norm plot of the log transformation of this particular column. And notice that it looks the data now looks better in that they are closer to the normal distribution. Right? The improvement is perhaps more so for the QQ norm plot on the right rather than the Q plot on the left, but still it's better. So if you're working with reaction times, you might want to consider this in your model, and you might want to apply this transformation. Now, because we know what we know now about the lack of normality of distribution for our reaction times, it's perhaps a good idea to fit a new model to not the reaction times themselves, but to the log transformation of the data that we have. So what you would do is you would ask R to create a new model, which we'll call model.example1.3. It is an LMER model, but instead of using RT as the dependent variable, which is the first thing we put in brackets, we're going to use the log transformation of the RT. So we're putting in log and in brackets RT. So that is take the RT and log transform it. Again, our independent variable would be condition, so ambiguous versus non-ambiguous, and we are adding it, and after that we would add in the random effect. So 1 plus condition vertical line subject plus 1 plus condition vertical line item. So we haven't done random intercepts, we're going straight to random slopes and intercepts. And again, we're using data.example1 as our data, which we do need to specify in the model. And we would summarize the model in exactly the same way as we've summarized the previous two models. We get the random effects on first, and below that we get the fixed effects. Since it's a random intercept plus slope model, we get the estimate for the variability in the random intercept by subject and by item, and for the random slope by subject and by item, which is the condition no comma row under intercept. So that's exactly like the second model that we ran in this session. And then below that, you can get the fixed effects, where again, you get the estimate, the standard error, the degrees of freedom, the t-value, and the p-value on the rightmost column. And again, you can see that they are significant. The p-values are well below 0.05. So in terms of interpreting whether there is a significant difference, for this particular data set, it doesn't make log transforming our data didn't make a difference. Now, one thing you might have noticed is that the numerical values for the estimate are radically different from what we got for the first two models. So notice that the change from unambiguous to ambiguous when we used the raw data was 140 to 150 milliseconds. Here, the estimate is 0.24205. Now, the reason we're getting estimates on a completely different scale is because you've log transformed the data. So that means that your data will now, the data, your dependent variable will be on a completely different scale. That shouldn't necessarily worry you. It just means that interpreting the estimate becomes less straightforward. So, as I said, log RT's leads, and in this particular case, have led to more normal residuals. So it suggests we should probably be using the, including the third model that we ran. Now, all the examples so far have been with reaction times, which is a numerical value. So the mixed effects models we've done are linear mixed effects models, in the same way that if we'd run a more traditional regression model, we'd have gone for a linear regression. But we can use mixed effects models for different types of data, in the same way that for non-mixed effects regression, we would have different types of regression. So imagine the same experiment, same participants, but with a different dependent variable. This time testing comprehension. So you give participants these sentences, same number of trials, but you also include a comprehension question, such as, for this particular example, did Anna dress the baby, yes or no? And you expect participants to press a button to indicate one of these two answers. And you can obviously know what the correct answer is, and you can judge whether participants have been correct or not. Now, the crucial thing here is that the dependent variable is a binary response. Participants' response will either be accurate or inaccurate, and that is what you're analyzing. You're not analyzing the reaction times anymore. In reality, you can do both, and most studies would actually have like a comprehension component for purposes of ensuring that participants pay attention and ensuring that the data are not impacted by noise that might arise from participants not paying attention. But in most studies, you would have, you could get both comprehension and reaction time measures. So if you wanted to, but say for the purposes of this webinar that we only have accuracy, if you want to have a look at the data, this is what it would look like. Again, you have data, multiple observations for the same subject and actually for the same condition. So again, you would have 3 data points for the no comma condition, 3 data points for the comma condition, and 1 data point for each of the items. But the response wouldn't be in reaction times, it would be 0 or 1. So 0 being inaccurate, 1 being accurate, and there's nothing in between or beyond that. Now, if you want to fit a model to test this, that's fine. But you won't use LMER, you would use GLMER as a function. Again, you would need to specify your dependent variable, which in this case won't be RT, it will be response. You would use the same syntax to specify the fixed effects, which in this case would be condition, and you would specify exactly the same random effect structure given that you have multiple observations, again by subject and by item. You would specify the data set, which in this case would be data.example2, because data.example1 includes the reaction times. One thing that you do need to be careful here is what comes after the last bit in this line of code, and that's family equals binomial. So what that does is it's kind of telling us that the dependent variable has a binomial distribution, so it's either 0 or 1. Because otherwise, if you don't, R will by default treat your dependent variable as linear, as far as I'm aware of, at least in most models that I've run. So if you do that, if you don't include this bit, it will basically think that all the zeros and ones that you've got are numeric values. So as I said, this code is similar to what we ran previously, with just 2 exceptions. We need to specify that the family is binomial, and we need to use GLMER instead of LMER. This is an example of, well, this is the output that we would get for this particular model. We'd be summarizing it in exactly the same way. We get random effects first, and that would be random intercept and random slope by subject and item, exactly as we've seen in the previous models. And then we would get the fixed effects beneath that. Notice that the intercept again is significant, and notice that the slope again is significant. So what this means in this case is that a change from in our independent variable, so from unambiguous to ambiguous, so comma to no comma, leads to a drop. So the estimate is negative, and that means that the likelihood of you getting it right decreases relative to the unambiguous controls. This is an example of a model failing to converge. So notice the last 2 lines, which says convergence code 0, okay, model failed to converge, blah, blah, blah. Now what this is an indication that we can't fit the model to the existing data set. It's just too complex, or you don't have enough variability in the data, or you simply don't have enough data. Now this can mean that when this happens, you can get some really wacky results and everything can be significant. You may find that actually the output is almost the same as models that do converge. So when you get a convergence message, normally you should not be reporting this model. You should try to simplify the model until you get one that actually does converge. So what you can do is, what we did in this particular case is we just removed the random slopes completely. So you can see we created model.example2.2, which is almost the same as the previous model, but we only have random intercept. So notice we have +1 vertical line subject, +1 plus condition vertical line item. So we took out the random slope for the subject and kept only the random intercept, but for the random effects by item, we kept both. And this model converged. So we didn't get any convergence messages. Again, we get the random effects and we get the fixed effects. And yeah, the estimates do change a bit every time you tweak the model slightly. But again, both the intercept and the slope are significant. We don't care that much about the intercept. Almost every intercept that I've seen is significantly different from 0. We care about the slope, the condition, no comma, because that indicates there is an effect of ambiguity. Ambiguous sentences are harder than unambiguous sentences. In this case, they've resulted in lower accuracy. And you've got a p-value here that is below 0.001. What do you so you run these analysis. What do you actually need to report? You need to report which type of mixed effects model was used. You need to specify, in other words, that you've included random intercepts random intercepts and slopes by subject and item. You don't normally have to report the output for these random intercepts and slopes. You can include that in the supplementary material in the appendices or online, but you do need to specify what the random effect structure was and that you simplified it when you had failure to convergence until you did get convergence. What you would need to describe is your dependent and independent variables, and for your dependent variables, you need to normally give the estimate, the standard error, the t-test or the z or the t-value or the z-value, and the p-value. If you've transformed your data, you need to mention that, and you also need to specify for your fixed effects how they were coded. So were they coded 0, 1? Were they coded as -1 + 1? Minus 0.5 plus 0.5, but we're not going to cover this in this seminar today. As I said, you don't need to report the estimates for the random effects in most papers, but you do need to specify what the overall structure was, and you need to report how you chose the random effect structure, what was the procedure of simplifying. Basically, you need to say that you took out those random effects that didn't contribute much to the variance. So there was not much point in having them there. Yes, as I said, for the model estimate, you do need to include the estimate, the standard error, the t or the z value, and the p-value. Also, because there's obviously a lot of information that you can't put in a regular paper, if you don't want to put everything in the appendices, you can make your data available online, and that would normally be platforms like GitHub or OSF. The stuff you would make online would be both your data and your analysis code, so that you could enable other people to go back and trace your steps. So it's not just a matter of there's too much information that needs to go in the paper. It's also, for purposes of transparency and replication, you enable others to check whether what you've done stands up, checks out. To do this, it's best to provide your data in an easily usable format. So best practice is TXT, and include the code for your analysis again in a TXT file. And here are some examples of how this has been done quite well on OSF. Now, to summarize, bilingualism researchers are often faced with data that pose particular challenges. We have a lot of variability in our samples, and the samples that we get are not necessarily reflective of the broader population. We have data that's clustered in either a nested or a crossed manner, and this means that the data are not independent. And if you don't take this into account in any form of modeling, you're very likely to get false positives. And you also have far more missing data or imbalanced data sets relative to research in monolinguals, especially adults. One way around it is to use mixed effects modeling. It can help you overcome these challenges, and it provides a useful tool to analyze a variety of types of data, both numeric and categorical, that have been investigated in bilingualism research. We haven't yet reached a consensus in that almost everybody agrees, but there are common practices, or at least sets of common practice. What is best practice is still evolving, and there's still debate, and there are empirical studies or studies using simulations that try to look at what results in the best model. I think ultimately justify your choices, be thorough and precise in reporting your analyses, and consider and making your data or code openly available. So it's not always about doing the best, but doing the very best you can and putting it out there in a way that it can be checked. Yes, it might be possible that you haven't fitted the best model, but that's okay. We don't always know what is the best model and what exactly would be the best thing to do. And here are some references if you want to read more into mixed effects modeling. We have a mailing list as well. And with that, I've finished. Thank you for your time, and thank you for paying attention. And so I'm going to stop sharing now.
Thank you very much, George, and thank you, Ian. We have plenty of questions in the Q&A that participants cannot see them yet, but we can as panelists. So did the two of you want to start answering those questions? So if you hit answer live, then our participants will also be able to see those questions.
Yeah, so we can go through some. I can go through some, George.
Yeah.
The ones asked, what should we report effect sizes for significant fixed effects? And if yes, what should we report from LME, and GLME?
Okay, so I mean that again would be dependent on the conventions that the journal might adopt. One way to do it would be a table with a summary table with all the fixed effects, and that would be, you know, one column with the actual effect and then separate columns for the estimate, the standard error, the T or Z value, and the p-value, which is something I've done in a few papers. You could include, and then in text, just mention the main effects, just specify which main effects were significant, say no other effects were significant. Or you could report in text every single effect and say effect A was significant, here are the estimates. Effect B was significant, here are the estimates in brackets. Effect C was not significant, here are the effects in the estimates in brackets.
I'd say the minimal thing you want to report is the model estimate, the standard, and the standard error basically is the minimal that you want to report for each effect. Let me find somebody's again. Can you please clarify again what is the difference between random intercept for subjects and random intercepts for items?
Okay, so if you the random intercept by subject is, let's say you've done this study with 40 people. It doesn't have to be 40, it could be 400, it could be just 20. The random intercept means that you accept that in the model that every single participant will have a different intercept, so a different average time overall, irrespective of the conditions. And then the random slope is that every participant will have a different slowdown moving from unambiguous to ambiguous sentences. So for some participants, it could be big, for some it could be small. The respective thing by item is that item is normally, I mean, in research that I've done that is normally with morphosyntax, it's the pairing of words that are used in each condition. So going back to the example, the ambiguous versus unambiguous sentences here, notice that they were exactly the same, barring the comma. So they involved exactly the same subject, exactly the same ambiguous noun phrase that we thought was an object but turned out to be a subject, and exactly the same verb. So Mary, the baby, and dressed respectively. So that pairing, for the purposes of this study, would be called an item. I've done a study with subject-object questions where we had questions like, which donkey is chasing the zebra? Which donkey is the zebra chasing? An example of item in this case would be donkey zebra chase, because we've used exactly the same words or exactly the same combination of words in both conditions. And we want to do this because we want the conditions to differ minimally other than the structure. And that's probably one of the most common forms of item you would have in psycholinguistic research. Ian, I'm not sure if you've...
Yeah, I would say it's not about necessarily by subjects or items, it's about the unit that you're trying to cluster your data in. So if you had students in classes, you would have a random intercept for each class. So it depends on whether you use subject, item, class, school, whatever. It depends on how the data is clustered in. In a standard psycholinguistic experiment, the data is clustered by subjects and by items.
Yeah. A random effect is basically a variable in that you've got multiple observations for it. So in the case of participants, you've got multiple observations of the same participant in each condition. And that means that your subject, your participant, is in his or her own right going to kind of become a variable, because there's going to be something about the idiosyncrasies of that person that's going to contribute to the reaction times across conditions. But what makes random effects different from fixed effects is that we don't really care about the fixed effects in terms of telling a story. It's not what we're actually testing. It's just that a random effect is anything that could be a variable because we've got data clustering, we've got repeated observations for each of its levels, but we're not really interested in treating it, in talking about it as a variable. We just have to take it into account that it is a kind of variable.
Someone else has asked, may I ask why for between subject or between item manipulations, random intercepts suffice? That's because when you have like a between subject variable, say you're doing a very basic lexical decision experiment where you're just interested, are native speakers quicker in a lexical decision experiment than non-natives? There is no condition slope to calculate. All you can do is calculate an average for an average for each participant and how that might randomly vary. So for that, you only need a random intercept. It doesn't make sense to fit a slope because there is no slope to fit. One thing I would say, if you have a mixed design, like you have some repeated measures and some between item variables, and this quite often happens, you might have a 2x2 mixed design, and then you have group as an additional factor. So you have 2x2x2, so you have 2 repeated measures and 1 between subjects factor. For any interaction with the between subjects factor, you don't need a random slope because the interaction is considered between subjects or items. Let me just try and pick some other ones. Right, this is a technical one to do with, we talked about failures to converge and model convergence issues. So if you get a singular fit or a failure to converge, are there any suggestive moves to deal with it, or just similar to convergence failures that we simplify model? Thanks. Singular fit, because Lima gives out different errors. Singular fit is normally, there's a bit of difficulty, but it's not terrible. But a failure to converge means it's really having difficulty. In each case, I would suggest to simplify the model, I think.
Yeah. From my experience, if you do get singular fit, also check the data. It might be that you haven't coded everything right, or that, I had an example earlier in spring with a data set that I got from somebody else. I kept getting singular fit, and I actually realized, and it was a model for accuracy, so accurate versus inaccurate trials with a rather complex fixed effect structure, but it turns out that I only had the accurate trials, and the end result is that when you're doing that for accuracy and you're expected to have zeros and ones, and you only have the ones, and you're asking it to compare what the likelihood is of getting a 0 as opposed to a 1 by condition, it can't estimate anything because everything is a 1. So you can't say that a sentence being ambiguous is going to increase the likelihood of you getting it wrong in a comprehension question when you don't have any trials where you didn't get it, where you got it wrong as a comprehension question. Does that make sense? So for you might also want to actually check that your data is as it should be when it comes to, if you get a singular fit. If you get failure to converge but non-singular fit, it's more of a problem with the model rather than the data, other than the fact the data is either not enough or not variable enough.
Okay, here's another, a few people have answered something about effect sizes. So follow-up question to the first question answered. So I said report the model estimate. So does this mean that the estimate value is the same as the effect size of a particular effect? So if asked to report an effect size, you don't report anything additional to the model output. I mean, it is an effect size, so you can report it as an effect size. Yeah. You might be asked to report a standardized effect size like Cohen's D, and it's not a standardized effect size in that respect. You
can calculate it. I mean, there are, as far as I'm aware, there are a couple of packages that allow you to get effect sizes for every particular effect within a model if you want. I can't remember which ones they are off the top of my head. Alternatively, there are certain mathematical equations that can basically take either a t-score or a z-score and convert it into a Cohen's D. As long as you know the standard error, which you do know, and the number of observations, which you can probably find. So there are some things you can do using software. There are some things you can do by hand. And then for confidence intervals, again, you can get them either through software, or you can just multiply the mean times by 1.96 plus 1.9 plus minus 1.96 times the standard error.
There was a similar question was how can you calculate the effect sizes and confidence intervals to the impact of the individual predictors in a mixed effects model? Is there anything to add to that?
Yeah, you'd apply the same calculation for every single coefficient that you've got, or if you use certain functions in additional packages, you just run the code more times and ask it once for the effect of the effect size for variable A, the effect size for variable B, and the effect size for variable C if you want. So doing multiple regression is just adding in more variables in terms of, writing code and then calculating effect sizes and confidence intervals.
Okay. There was one. Okay, so somebody said in some research I saw the random slopes, the random effects were defined as open bracket 0 plus condition down subjects. Could you explain the difference between using a 1 or a 0 in your random effects?
Yes, it's actually not the one itself. It's actually that the entire thing is shorthand. So when you have 1 plus variable, what you're saying is allow for a random a random intercept plus a random slope. That is actually shorthand for two things put together. One is the one vertical line subject, which is only the random intercept, but also it includes the 0 plus variable vertical line subject, which is the random slope only. So in the notation that we used for the models that included random slopes, we basically said 1 plus condition vertical line subject, that is allow for both a random intercept and a random slope. We could have just added two separate terms, one vertical line plus subject plus 0 within brackets 0 plus variable vertical line subject, which means allow for one is allow for both, the other one is allow for one and then a separate term to allow for the other.
If people have 0 plus slope by subjects, they're trying to suppress the intercept basically, and they might be doing that because the model didn't fail to converge, and in that case they found that the slope accounted for more variance than the intercept, so they decided to remove the intercept rather than the slope. Yeah.
So yeah, when you see this, it's normally that when you break down this shorthand, it's because you want to be more specific about the model. So don't include everything because everything didn't work. So start being more selective.
Somebody's asked, what is the importance of the correlation between the random intercept and the random slope, and what motivation would one have to remove the correlation except to simplify the model? So this is really just showing that trying to model that there can be a correlation between intercepts and slopes. And I think your data showed that quite clearly in that people that were overall slower showed larger effect sizes, and that's what you often see. And so the model is just trying to account for that variance. What you do often get is the models have difficulty estimating these correlations. So you get values of either 1 or -1 as if they are entirely correlated. In reality, the values won't be that highly correlated. It just means the model's having difficulty fitting it. What you often get very high correlations if the random slope accounts for little variance on top of the intercept, I think, in my experience. And that would also be a case for removing the random correlation to simplify the analysis. Especially, I find removing the random correlation helps a lot in terms of convergence errors, because it's the correlation often causes difficulty. Yeah, as somebody just said, if you get a correlation of 1 of a random slope, do you remove the slope? I mean, some people would say that. I would say if the model doesn't converge, that is possibly the first thing I would look into removing to see if it converges, basically. Right, I'll just try and find it. So, right, a few people have asked about, let me see, about coding schemes. So this is something we didn't have time to talk about because we ran out of time. So one person's asked, could you please talk to us more about contrast code versus sum coding the variables so we can properly interpret the results? And then somebody else, Anna Maria, has asked, in all the examples you use treatment coding, however, sum coding is widespread. Could you say more about the advantages of using treatment versus sum coding? I would say it's difficult to get into this. What I will do is there are various papers and blog posts on the internet that go into this in detail. So what I'll do is I'll put some links in the chat for those of you interested. The one thing I would say about coding schemes is that there are different. We often don't think about this when we do an ANOVA, but if you do a multiple regression or a logistic regression, we think about that a bit more, but actually you can think about it whatever analysis you're doing. And the important thing to remember is that the default coding scheme that you get in R is not the coding scheme that you would get if you did an analysis in SPSS. So the default coding scheme doesn't give you main effects, it gives you something called simple effects, which are interpreted differently. So be careful if you haven't changed the coding scheme, be careful in how you interpret your results from R. I think given the time, it's difficult to go into it in any more detail, but I will put some links into the chat that hopefully explain this in a bit more detail.
Also, you'll be able to see based on the output that you get. So for what we used, which was 0, 1 for our independent variable, when you get the output, it will normally give you the slope, and it will give you something, as you saw, condition no comma, which suggests that the change to no comma from comma results in the increase in reaction times. If you apply like contrast coding, you won't get that no comma. So that should function as a hint that you know as to how things have been coded, and it could get you wondering as to whether you've coded them correctly or not, or appropriately or not.
In terms of links, somebody has also asked, can you put a link for the mailing list in the chat again? I'll in a minute, I'll try and find some links, and I'll add a link to the mailing list as well. Okay, here's a fairly long question that I'll try and go through. I can answer this one. So assume that I ran 2 reaction time experiments that had exactly the same procedure and had 2 conditions. So had 2 factors, factor A and factor B. So you have 2 main effects and an interaction, so A star B. So the maximal model would be A star B, and then you'd have random slopes for A and B by subject and by item. Say I had 2 experiments that had different items that were comparing, say, subject versus object relative clauses and different participants. Would it be okay to analyze the data from the 2 experiments in one model to see whether this difference between experiments is actually significant? Yes, that's perfectly fine. That's actually something I do quite frequently. If I'm reporting an experiment, if I'm reporting a paper with more than one experiment and I'm trying to draw conclusions across experiments, I try and do a between experiment analysis. So you can always combine the data from 2 experiments and have experiment, or have experiment as a factor and compare the 2. One thing I'd say here is you need to be careful about how you think about your random effects, your random slopes. If you have completely different participants across experiments, then your factor for your experiment, you don't need to include a random slope for that, because it's effectively because it is a between subject. It is a between subject manipulation. For your items, if they're completely different items, again, you wouldn't need a random slope for experiments. If you've basically got the same items and you've kind of manipulated it within an experiment, like in George's example, where we've got the same sentences just with or without a comma, or say you're looking at subject versus object relative clauses, you have exactly the same sentences, except you just have a subject versus an object. If you're treating that as a repeated measure, then in the items, you could potentially include a random slope for experiments. But yes, in general, you can do between experiment analyses. Just think about whether the particular factor has been manipulated within or between a unit at the level of the experiment. Somebody has also asked, if we have a 3x2 or any sort of repeated measures design, and we have 2 independent variables and their interaction, if the interaction effect is significant, is it required to run post hoc analyses, for example, e-means? I would say yes, run a post hoc analysis. There are some packages that do the Bonferroni correction. What I typically do is I would run a second model with what's called nested contrast, which basically compare the conditions that I'm interested in to get the follow-up analysis. Okay, there's quite a few. Let me just see any more. So a few people have asked, so for example, one person's asked, can you just go over again why I would switch between LMER and GLMER? And somebody has also said, may I know how we can determine which family of function to use when running GLM or GLMER? So should I use Gaussian, quasi, Poisson, etc.?
That would depend on the nature of the independent variable. So you'd want to use Gaussian or inverse Gaussian for things like reaction times, where you have numeric, basically numbers. You'd want to use Poisson for where you have counts, so where you have numbers, but where you have discrete numbers, so you can't have 1.5 and you can't have negative values. You'd use binomial if you have categorical, an independent variable with categorical value, so yes or no, right or wrong, dead or alive. You'd use multinomial for where you would have categorical responses, but you can have more than two, so yes, no, not sure, agree, strongly agree, disagree, strongly disagree, neither.
Yeah,
and each of these...
You need to think about the distribution of your dependent variable and then pick a one that's appropriate.
Yeah. The nature of your variable actually has implications for the assumptions you're going to make about the distribution of the variable, because you can't have, for example, a standard deviation for binomial responses. You get the responses there and there. There's no bell curve, which is why you can't use a Gaussian distribution for that.
Okay, we're running out of time, so I think we'll do one more question. I should say, if we have space at the end of the entire workshop, we can come back to some of these questions. But for now, we'll ask one more question about data-driven and theory-driven approaches. So you mentioned if your study is more exploratory, you can choose a data-driven approach. I'd say yes, that's true. It's just because if it's truly exploratory, you may have so many variables that fitting the maximal model just becomes impractical or impossible. So, for example, in an L2 study where researchers aim to replicate an L1 study with an L2 population, can one take the keep it maximum approach for the already tested effects, for example, in the L1 studies for replication purposes, and use a data-driven approach for a series of L2 proficiency tasks? I think here for me, it would depend on what your research question is. If your research question is really about proficiency, you may want to include the maximal model. If you're really interested in the effects previously reported, you might want to keep it maximal for the effects previously reported and then include a random slope for the proficiency task. I would say it's always more important to really test whether there's a random slope. If you're making a claim that a certain fixed effect, in this case proficiency, is significant, you should at least try and see if the random slope improves fit. So you should at least look to see if you need to include the random slope. I think that's what I would say.
Okay, thank you very much. I think we need to take a 5-minute break before the next session, which I will start playing the video from my side. As Ian said, there may be time to answer some of the remaining questions towards the end of the second session of Q&A. We have at least another 10 pending questions. Some of them are duplicates. I'll clear off the duplicates. The other thing I should have mentioned is that with George, Ian, Stefano, and Joao, we are preparing a special issue on these exact topics that will appear in journal Linguistic Approach to Bilingualism sometime in early 2025, I believe. So there will be more opportunities for you to read about these topics. So, okay, seems like we have 3 minutes before I start the next session. So let's take a break now.